my name is Max, and today I have a bit of an interesting puzzle for you. I was originally given this by a good friend's family, and after I'd solved it, it sat on my mind for a long while, and I began handing it out to some of my friends and family. The basis of the problem is, we have a little ant in this grid that needs to navigate to a pile of sugar in the opposite corner to him. However, our little ant can only move in steps of one, either down or to the right, and he must repeat these steps until he reaches the sugar pile. However, there are a few red walls which he cannot cross. Now, the actual problem in this case is in how many different ways can our ant make it to the sugar. I'm sure that a few of you have already begun tracing them in your minds, and I'm going to draw out a few paths just to show you that the ant can indeed make it to the sugar. I think that by inspection of this problem, you can see that there's a lot of paths that we haven't drawn in, and if you're thinking about it, there's probably a lot of paths that we're just not going to be able to draw out, or we're not going to be able to keep track of all of them because there's going to be a lot of paths. So, in order to solve this problem, I'd suggest we move on to something back from grade 8, Pascal's triangle. Now, I'm sure you all remember that Pascal's triangle begins with just a 1 floating in space, and that every number given in Pascal's triangle is the sum of the two numbers directly to the top left and the top right of it. So, for example here, when we have 1 and 1, they would sum to 2, and 1 and 2 are going to sum to 3. So we'd have 3 there, and so on and so forth. Now, if we keep filling out this table, I think it's eventually going to look something like this. And now you might recall from high school or from some other place that this is also a nice representation of the number of ways we can select a certain number of things from a much larger population. For example, if we look down here at the 4th row, so the row that is 1, 3, 3, 1, here we can see that if we had 3 objects, 1 is the number of ways we'd be able to select none of them, 3 is the number of ways that we'd be able to select 1 of them, 3 again is the number of ways that we could select 2 of them, and 1 is the number of ways in which we could select 3 of them. Now, this is all well and good, but it doesn't really explain why this happens or what it has anything to do with our problem. So, I'd like to move on to a nice new explanation. So, you remember that we were talking about just selecting objects from a bigger series of objects, but that's generally something that's quite hard to visualize or make out in your head. So, for this example, I'd like to imagine that we're making an ice cream, right? We've got an ice cream cone, and we want to have a combination of either chocolate, vanilla, strawberry, or mint on the top. Now, we could go extreme, we could have 3 flavors, or we could have 4 flavors. And now, for the purpose of combinations, right? We're just gonna say that if we have a vanilla and a chocolate, it's the same thing as having chocolate and vanilla. It's the same combination of flavors, they're just in a different order. Okay, so what I want you to imagine is you want to make this dream ice cream of yours with chocolate, vanilla, strawberry, and mint. And so there's a server standing in front of you with a container of chocolate, a container of vanilla, a container of strawberry, and a container of mint. And he's going to ask you, okay, so would you like some chocolate on your cone? And now we're going to look at Pascal's triangle to try and represent this. So we'll start off in that top square there, where there's nothing and there's 2 arrows leading down. That represents we haven't been asked anything and we haven't chosen anything. Now we're going to be asked if we want chocolate, and we can choose either to say yes, I would like a scoop of chocolate and move down to the right, or we can say no, I would not like a scoop of chocolate and move down to the left. But either way here, you can see that if we choose a scoop of chocolate, that's just going to be represented by the brown circle. And now we've chosen if we want chocolate, the next logical step is, hey, now we've chosen that, do you want some vanilla on your cone? And again, we're going to represent this with a triangle, just the other one with an extra row added onto it. So you can see if we'd chosen chocolate previously, we would be ending up in that second square on the right. And now we can choose whether we want to add vanilla as well. So we could choose again to add vanilla, go down to the right, and then we'd have chocolate and vanilla on our cone. But now you can also see that center bottom square has 2 different ways we could have 1 scoop. We could either have 1 scoop of chocolate and 1 scoop of vanilla. And another thing I want you to realize is that's also the number of ways we could have gotten to that square. We could have chosen to have either chocolate and then no vanilla, or vanilla and no chocolate. So that's kind of already relating to Pascal's triangle quite a bit, as you can probably see. Now let's move on to the next step, right? You've just had chocolate and you've just had vanilla, and now we want to choose whether they want to have strawberry. So again, here you can see we could choose to have strawberry, it's going down to the right, or we could choose not to have strawberry and going down to the left. And now I hope you can see, again, this is relating to Pascal's triangle quite a lot. If you recall, the third row is 1, 3, 3, 1. And here we can see we only have one way of choosing no flavors. We have three ways of choosing one flavor, which were chocolate, vanilla, and strawberry. And we also have three ways of selecting whether we want two flavors, which is chocolate and strawberry, chocolate and vanilla, or vanilla and strawberry. And then there's only one way of having all three flavors. Now, we've chosen three of our flavors. Now we have to move on to the fourth flavor, which is mint. And now what I want you to kind of recognize here is that those three squares above the bottom center one, right, I'll circle them here, are chocolate, vanilla, and strawberry. And now we're making the decision with mint, right? So if we go down and to the right, that's going to be adding mint. And you can see those three combinations are reflected there, right? We now have chocolate and mint, mint and vanilla, or strawberry and mint. And now if we look at the other three flavors that we already had, which were combinations of two, if we choose not to add any mint to those, we're going to go down to the left with these three, and then we're going to see that they add up to these three, right? Which are just exactly the same ones, not adding mint. And so you can see there that all the combinations on the top left are going to propagate to that square down below them by adding the item, and all the squares in the top right of that square are going to go down into them by not adding the mint. And so you can kind of see again that this is the number of paths that lead to this square, and this is the number of combinations that are going to be represented in this square. Now I want you to just, again, soak in Pascal's triangle, soak in the beauty and the grace of it. So now we've kind of recognized that each number on a square is the number of paths possible to get to that square, and it's the number of combinations choosing from a certain amount of items. So now let's just represent that graphically. So we'll start here at 1. There's one way to get to each one of these, but there are two ways to get to this 2. And so on and so forth. There's only one way to get to all of these 1s. There's 3 ways to get to both of these 3s. And then there's 4 ways to get to the 4, because there was one way to get to the 1 and 3 ways to get to the 3. And then to get to this 6, there's going to be 3 ways plus 3 ways, which we already saw with choosing our ice cream. So now we're just going to redraw Pascal's triangle in this nice form, right? I hope that you can understand it's, again, exactly the same thing, just redrawn in a diamond kind of shape instead of a square. And now let's test our hypotheses one last time before we move on to actually solving the initial problem. So let's just look at this square, right? Let's say, okay, how many different ways could we get to this bottom square that's highlighted in red? Now the value of that square is 6. So let's just use our hypothesis and say, okay, there were 6 ways of getting there. And now we'll just draw them all out for you. So let's say there's 1 way, there's 2 ways, there's 3 ways, 4 ways, 5 ways, and 6 ways. And then again, there's no other ways that we could have gotten there. You'll notice that it holds to all the rules we just talked about and went over. So yeah, this kind of shows us that this is the number of ways we could get to 6. So now I want you to have a think about this initial problem. This would be a great time to pause the video and come back when you think you've solved it using these methods we've found. Either way, I'll give you a few seconds and then I'll reveal the solution. Now, the first thing that I'd do to solve this puzzle would be to fill out the first row of our mini Pascal's triangle as such. And that would be saying the ant can go to this square once and this square once. And then I'd take the next step and fill out the second row, show that it can again go down to the left in only one way. It can reach that square directly under the ant in 2 ways. And of course that square behind the barrier, it can be reached in 0 ways, because these numbers can't be added up across barriers because you can't cross barriers. And then again, I'd fill out the third row just like this with 1, 3, and then again 0 and 0 because you can't reach it. And by using this method and filling it out one row at a time, you'll eventually get to this final solution, where you can see that the total number of ways to get to the end is 88 different ways. Now you can pause the video and count these up yourself, double check my maths, why not? But I think this is a really nice, elegant solution to this problem, which solves it using very easy to understand and basic mathematics, but applied in a very intuitive and easy to understand way. Now, I know this is very cliche, but thank you for watching my video. I hope that it helped you understand the maths a bit better, and I really hope that you enjoyed it.